Okay, I guess we'll get started here. Hopefully everyone can hear me. Well, those of you that just joined us, check out the QR code to download some of the files from today. Maybe I'll ask your class what's the course 461. Okay, who has an interesting experience that they've had in this class, something that you've learned, or something even from co-op that you've applied that made you come to this session today? Who wants to share a quick story? Or are you all just bewildered by analysis in general? Yeah, go ahead. Sure. Okay. Okay, that's a very interesting topic. I was going to bring it today, but the heat is on in my house. I recently moved to a new location, and the ductwork that's in the flooring of the house is a fairly old house, so it had a retrofit of air conditioning and heating, and it blew right against the window. So half of the room is hot, half of the room is cold. So myself being an engineer, much like all of you, I couldn't sleep at night knowing that. So I 3D printed a duct guide vane that kind of went inside, and it was all designed in the software packages that you're going to see today to get even distribution of heat in the room. So prior to that, it was uncomfortable sitting on one side of the room, and now kind of the whole house is homogeneous in temperature. So that made a big difference. It's a practical application of kind of what we're looking at today. Does anybody have another example on your fourth year project that you can foresee yourself applying some form of simulation? Yep, go ahead. So thermal analysis is a common thing fire research uses a lot of computational fluid dynamics. So I guess I should introduce myself. My name is Andrew Raguch. I'm a faculty member in the mechanical and mechatronics engineering department, so please don't hold that against me. But a lot of the examples I'm going to give you are kind of more mechanically intensive, so they're not directly dealing with fire, but I'll show you and I'll give you the tools that will enable you to kind of think in a way that everything in your life is going to look like something you can simulate from now on. So it's kind of a vice or a curse in that respect. But the way I'll start, I guess the agenda for today quickly is I'll talk about a motivation and overview. So I've kind of led into that, hopefully extracting a little bit of your desire to be here already. But I'm going to go over a shotgun blast of information, kind of from my background professionally as well as research wise. That's going to give you a very broad overview without you understanding anything about it. It's going to give you a very broad overview of what analysis can do, the different types of domains that you can analyze, what different procedures for analyzing things are, and what's even possible. And I'm not going to say this is state of the art. I worked as a engineering analyst for about 10 years in industry up until maybe I started here about 8 or 9 years ago. So it it has progressed a little bit since then for sure, but I'll give you an example of some of the things that I did in industry. I teach a graduate course that's kind of intensively using analysis, and I'll give you some examples of work that my students have done, which frankly is quite amazing considering the time constraints that they're held to. So that's kind of the first part of the lecture where I'm just going to wow you with information. It's going to be a lot of pretty pictures. I'm not going to explain in detail exactly how the analysis was set up. I just kind of want to motivate you and kind of trigger your subconscious mind to be like 3 months from now when you're thinking, is this possible? Oh, I remember in that TDM, the professor talked about this type of analysis. That's a thing I should do more research on. Okay. After that, we're going to talk about like the actual theory behind finite element and computational fluid dynamics. And I promise I'll make it interesting and it's not going to be dry and boring. Um, and then we'll do some case studies on some best practices, showing different analysis procedures for different simplistic problems. And then we'll actually open up some CAD files in SolidWorks, and you'll get a chance to simply apply boundary conditions, loading, things like that, where and then run the simulation. So that's something that maybe 10 years ago, if you were to do a live lecture, it would be impossible to do. Now everyone has enough power in their laptop to run these simulations in seconds. So you get that instant gratification kind of endorphin hit when you see the results. But I'll talk about how everything needs to be qualified. This is a really cliche saying, but a lot of people refer to simulation in general as garbage in, garbage out. Okay, you'll get a pretty picture at the end of it if it converges, but just because it converges doesn't mean the result that you're getting is sensical, logical, safe, accurate, any of those things. So the onus is on you as the engineer to kind of deal with verifying and qualifying all of those things. So I worked in the automotive industry for 10 years. This is a screenshot from a typical meeting that I would be in. It's probably something a little bit more complex. It's a CAD model of a front suspension of a vehicle. I know a very mechanically intensive example, but you should have all probably been exposed to something like this. You've all used CAD casually, maybe on your co-op, maybe for your fourth year design project, but things like this exist to describe geometries in the digital world. Okay, this is the modern era of an engineer. This is type of things that you'd be looking at, and you can see that there's different components here. They're all rendered and shaded differently, and you can see that there's a part here that steers this part of the suspension that's connected to the tire. This is what supports the loading of the vehicle. This is one particular corner, and you can see how it all interfaces with kind of the structure of the vehicle. So I'm not too concerned with the actual example here, but I want to use it as kind of a stepping stone to understand different things about analysis. So to talk about some structural simulations, this is what people most traditionally think of analysis. Here's an example of a project that I worked on for a steering column of a vehicle. So this kind of looks like a crude representation of a car, but you can kind of see the part where your feet go, where the pedals would be. You can obviously see a steering wheel, and you can see all the structure that's behind the nice infotainment and all of the radio controls and the HVAC system in the car. You can see all the structure that's behind it. And a lot of people just take for granted, like, why is that even there? To hold up the weight, maybe of the steering wheel, so it doesn't vibrate in your hands, and it's obviously probably allowing you to adjust it for different drivers, different sizes. But the most important thing is that that protects the car. It's providing structural integrity in a collision. Okay, so here's an example of if you T-bone somebody, that's a pretty casual or colloquial term to describe an accident. But if you hit someone head on, the front of the car is going to crumple and it's going to push the steering wheel into your body. So this is kind of simulating that type of event. Okay, so you can see part of this structure here actually meant to trigger and buckle to allow the crumpling to happen. Okay, and the part that's holding the steering wheel, you kind of want to limit the amount of movement that's there because the airbag is obviously there to cushion the blow between your torso and the hard parts of the vehicle. So here's an example of something like that. Here's a top view of the same thing, so you can kind of see how the whole structure is moving. This one people like to see if you ever got hit from the side. So if you were the person getting T-boned here, this is a pretty scary, let's say, animation to look at. But this is a simulation of the entire structure kind of crumpling in on itself laterally. Okay, and you can see that some of this buckling that's happening here. So that's kind of that uncontrolled displacement. A lot of you mode is called buckling, which is undesirable because it pushes all of the stuff that's in front of you when you're sitting in the vehicle. It'll push it into your occupant part of the car, and it could obviously cause injury. So a more desirable, let's say, deformation mode here would just be for it to crumple in on itself. So that's something that we achieved with changing the actual geometry of this tube that's actually holding the structure of this part of the car. So that kind of gives you an example there. People think that the car is symmetric. Okay, if you get hit from the left, it's better than getting hit from the right. In this case, it's actually worse. You'll probably sustain more injuries if you get hit from the passenger side just because of the way that the existing structure would buckle. It would probably push more of the content into the driver's side if you were the one driving the car. But in the revised design, I should have mentioned the top is kind of the baseline, the bottom is kind of the optimized one. You can see how nice and neatly and compactly it just crumples in on itself. Here's an example of a suspension component. So this is like a structural part of the actual car that holds the wheel to the frame. You can see here, if you were to hit a pothole really hard, this is kind of like a simulation of how the part would actually buckle and break. Okay. So a lot of times you'll see when people show stuff like this, you'll kind of see the thing on repeat or rewind, and it's an animation showing kind of the whole cycle of the event that you're simulating. Okay, and it's just showing it on repeat because you can kind of see it as an animation in this case. People like to see this, and this is often why people show up to sessions such as this, is because there's a lot of more modern techniques. I say modern, but these have existed for 15, 20 years now on what's called topology optimization, or using machine learning to optimize the design intelligently to remove material where it's not necessary. So for that similar type of component that you might have this triangulated structural member, you might say, okay, well, here's the entire volume of material that we're going to start with. This is the possibility that in terms of volume where the design can exist. So you might have some cutouts where, okay, it can't go past here. You can't grow any past here. There's some interference with another component over here. So we want to force it to kind of stay within this box, this design volume is what it's called. Parts that interface with kind of other parts of the design that you don't want to change. So you can see here the 3 locations where it's touching other, let's say, components. Those are not evolving over time, but you can see the algorithm will iterate and effectively look at areas with low stress, and it will remove them or kind of vary the density. It'll start lowering the density of those parts of the design or parts of the component until they effectively do nothing. Okay, and then you can whittle away the material and develop these load paths within the component that allows you to have a really mass optimized design and these nice organic shapes that intuitively you really wouldn't think about. Okay. Here's an example of looking at that density change. So areas of red are very high density, areas of blue are, I think, 50% density, and anything that's transparent is lower than 50%. So a lot of people think that this topology optimization or using machine learning to kind of do these analysis type procedures, they think you're going to just get the answer out of the end of it. Okay. And unfortunately, we don't live in a world where that's possible yet. Often, you as the engineer, you have to interpret the result that you, and you have to then go and kind of morph the surfaces and create the geometry to using this as a guide. So here it's obvious that there needs to be some lightning holes and cutouts in certain locations, depending on how you're applying the loads and what the constraints are and things like that. And I know this is like a real big, overwhelming amount of information so far, and it's going to be even more overwhelming as I go through slide by slide for at least the first 40 minutes. And if you have questions, feel free to raise your hands and really be like, oh, I wonder what this means. Can you explain it a little more? But I'm going to explain the theory after I'm doing this lecture a little bit backwards because I want you to get excited about the possibilities here before you actually understand and get bogged down with the details of how it works. Here's another example of a type of shape optimization where you might have a component that needs to connect point A and point B here, like you can see with the cursor. But unfortunately, there's another component in between, so you can't have a nice straight shot to that. So you want to figure out a way that you can effectively grow the geometry in such a way that it meets the structural requirements without compromising on this volume here. So you have to grow it downwards in order to make it work in this case. Here's an example of an operation where you're simulating. This is kind of like a ball and socket joint that you would have in your hip. This is obviously made of metal in this case, but it's looking at, now we're not looking at just like a very static type simulation where there's a load and the material is just deforming. In this case, there's a lot of gross deformation. Gross meaning very large macro scale deformation. You're peeling apart components and actually getting them to fail in this case. So this is looking at the amount of load it takes to pull this ball out of the socket effectively. So how, to put it in another way, how much force it would take to dislocate this joint. If you've ever dislocated your shoulder or another type of joint, you can imagine how painful that is. And we don't have the luxury of doing this in real life, but this is pushing it back in this case. So how much actual force it would take to do something like that. Some of you are interested in fluid dynamics. What I did for my fourth year design project was I designed a centrifugal compressor. This was many years ago, like almost 2 decades ago now, but I did it as part of a student team, so that was pretty cool. But I looked at what's called modal analysis. So I looked at the vibration kind of characteristics of this compressor because it spins very, very fast. In this case, it's used as a kind of a device that converts kinetic energy and it recovers it into pressure. So it's compressing the air by spinning it really fast, imparting a lot of kinetic energy into the fluid. And then there's a scroll diffuser that actually recovers it as pressure. So if you didn't like your fluid mechanics course, you might not like these next slides, but this was kind of state of the art, I guess, 15, 16 years ago now. But it's pretty easy to do. You could probably even simulate something like this in the lecture. So here are some of the, this is what's called like a setup slide or something like that. It's defining all of the different boundary conditions of the control volume that I was using for this particular simulation. Here's a nice pretty animation showing the swirling of the air going into this compressor, and you can see how it's going to kind of go into the part where the blades are, and it's then going to accelerate very quickly on the outlet. So you can kind of see a lot of these are slides that have a lot of pretty colors and what are called contour maps, and these are streamlines showing velocity here. But effectively, it's just a visual way to look at data. Okay, so we're using the colors to represent magnitudes of different quantities. In this case, it's velocity. In this case, on the bottom left, it's pressure. And on the top, it's actually temperature. Here's another example of airflow through a duct with some time varying information. So there's an inlet and an outlet, and the air goes from one side to the other. Here's another example of something. I worked on a project back when a Jeep looked like that, where the structure of a Jeep has these bars that effectively maintain the roof from collapsing when you flip it over. In the event that you get in an accident, unfortunately, you'd tip over the car. So these bars actually run kind of the length of the side of the car, and they're fairly difficult to make. The reason being is you don't want something that has some inherent kinks in it. If you've ever tried to take a tube and bend it, or even like a piece of plastic tube would be very easy to do, you might imagine that if you bend it too tightly, it'll start to kink. So this process here is actually a really cool process where that we simulated it to kind of come up with it, where you hot form the part. It's a tube that you heat up really almost to the point where it's cherry red, and then you inflate it with air to kind of iron out all of the wrinkles. So here's an example of the part as it gets kind of bent. You can see all the wrinkles that are forming, and then it gets pumped full of air at a very high pressure. And because it's at such a high temperature, it actually inflates like a balloon, and you get a nice tubular part that conforms to the shape of whatever you kind of want. Yes, question. A little bit of both. That's an excellent question. If you remember, I don't know what your solid mechanics course would have looked like, but if you remember like an I-beam, so if you take a structure that has some cross-sectional properties, if you put some defect in it, no matter what you do when you bend it, it's going to kind of initiate a failure in that location. So part of it is aesthetic. A lot of this is covered now with plastic in cars, so you don't really see it, but a lot of it is aesthetic, but some of it has to do with structure as well. So very good question. Here's an example of simulating kind of a process where you take a flat sheet and you can change it into these interesting shapes for like this kind of looks like a hockey stick, but it's actually another suspension component for a car. So each of these operations where you kind of indent it with this rib and you make this flange on the side and then you pierce these holes and you turn it into this W shape. And I'll show you the entire animation here where you start with this flat sheet, you indent the middle, and then you kind of start to create a flange all the way around. You trim it a little bit. So there's opportunity to do entire process modeling in this. So um, one of your colleagues here mentioned about, I guess, fire modeling of what was the component or what was the system? A sensor box. So you could do the ignition proceed or the ignition phase, and you could do the spreading phase, and then the steady state fire perform or steady state kind of fire level or performance of that particular type of situation. So there's stages to this. You can do a moment in time, or you can do kind of the entire process. Here's an example of another vehicle. If you've ever been on one of the GRT buses and you've ever felt it come to a stoplight and the driver puts their foot on the brake, if you're sitting in the wrong spot of the bus and you're listening to music or you're on your phone or whatever, you might have noticed that a lot of things tend to vibrate, especially seats and things, handles. You'll feel it through your hands. That's undesirable. They don't really care so much in terms of public transportation, but for consumer products, generally you want to limit kind of that amount of vibration. So there's a lot of or I guess a lot of effort that's put in to do stuff like that. So this is an example of a very exaggerated vibration mode. So you're looking at kind of a vertical motion of the steering wheel and a lateral motion and how to kind of optimize it. So this is what's called an NVH or noise, vibration, and harshness simulation. So it's not really looking at the failure of anything. It's looking at how it will move when you excite it with some random frequency. Some frequencies are very damaging. Some frequencies aren't so bad. So you notice that when the bus driver takes off and they start moving, often the vibration will change, and sometimes it'll even go away. Skip through this slide. Here's an example of an entire vehicle, that same Jeep structure with those same parts that we were just talking about how to make. You kind of want to worry about how the entire vehicle is going to twist in a situation. So I'll talk about another simulation for a student team where they actually did a similar simulation. It was FSAE, but here's an example of the entire structure of a vehicle kind of twisting. And you can see a different view or a different angle of it right here as well. The most important thing, in my opinion, is what's called, and this is something that kind of defines a good engineer from just a mediocre one, in my opinion, and even something that is safe and accurate, is the correlation between the analysis and a physical experiment. So a lot of you that are doing a fourth year design project, that's often the biggest criticism that you'll get. I've been a judge for ANSYS, who's a company that makes competing software to SolidWorks, which you're all familiar with. They do a design competition where every year, and I think Systems actually won last year. I'm not trying to remember, but there was a project from Systems that was excellent. But I've been in touch for that for a long time, and often the biggest concern that I have is students do some form of simulation and then they look at the results and they're like, that's it. My first simulation was perfect. This is the gospel now. I need to take this as being true and it's 100% accurate because it looks legitimate. And without any qualification or correlation between reality and virtual world. Okay. So here's an example of a physical test video overlaid beside or not quite overlaid, but just beside a simulation of the same thing. And you can see the way that this part is actually crushing is very similar between the two. And if you get picky and you look at the actual measurement of the movement and everything, it's like within 2 or 3%. Okay, so you can get quite close, and this is you can get even closer than that depending on the complexity of the movement or the complexity of the temperature field or the flow path or whatever you're looking at. It really depends on how much detail you model it with. The more detail, the more complexity, the longer runtime, the more headaches on your end as the engineer. But often you're able to capture parts of the physics and kind of the actual motion that are really nuanced behavior of the component. So here's a good example of that. That was my previous life in an engineering analyst job, but part of what I do now as a prof in the mechanical department, I teach a grad course where students kind of look at projects that intensively use analysis, and they come up with a design, kind of like fourth year design project, but they use existing designs and they just analyze something. So this was a bearing test machine that actually was developed in the Ideas Clinic here on campus as part of like a dynamics course lab. So a student looked at this, and it's a machine that has a motor that spins a shaft, and there's bearings inside. There's these ball bearings inside, and the student actually drew a CAD model of it, and they wanted to look at how the bearings were moving. So they decided to do a model of the shaft in ANSYS, which I'll show you a little bit of as well, but mainly we're going to be focusing on SolidWorks. And here are some of the setup parameters of that shaft. And then they looked at, okay, well, how are the ball bearings physically moving inside that bearing? And you can do stuff to this level of detail. So they modeled all of that as well. So they modeled the carrier, the kind of part that contains all of these balls, and it rides within this metal kind of outer housing. And then they put it in the larger assembly. And then they kind of did a simulation here that looked at all of it. So here's an example of something like that. Something that I think in second year systems now they're doing in, forget the name of the course, I think it's 286 maybe, but they're doing it in kind of a materials test setup where you look at different deformation modes, and there's a physical experiment, and it's kind of linked to this simulation environment where you have a virtual twin of the exact same component. So here are three examples, or sorry, four examples. This one is a typical test where you're pulling on something, and you can see the stresses is what you're seeing here. Oops, sorry. The stresses are what you're seeing here in the middle. So this is like a dog bone type experiment that you'd see in material science. This one is like a typical diving board, so it's just a cylindrical, or sorry, a rectangular strip that's been bending. We're actually going to be doing this one today, and I'll show you exactly how that works. You're going to be creating this model from scratch. It's really easy and quick. The next one is a rod that's in torsion. So in this case, this rod is getting clamped in a kind of a test setup, so you can see kind of the displacement here. And then the final one is a spring that's also in tension here. And we'll look at something similar to this as well. Another thing that we looked at in during COVID was a student was stuck in their dorm room, and they had an idea of, oh, I want to simulate the motion of this IKEA chair, because I don't know if they were sitting on it in a way that was really weird. This is the Poang chair from IKEA. Probably a ton of you have it. You did this project. Okay, okay. Maybe you like it, maybe you don't, but we simulated a lot of this. This is me sitting in my basement actually with a chair. You can see that I put some LEDs on it to track some motion in three different locations. Apologies for the poor lighting, but you can see how the chair is moving when I sit on it. The cool thing is we actually simulated half of the chair here, and we found the stresses and the displacements. And this is kind of the proof that's in the pudding, where you can see the simulation when you overlay on the physical chair. The displacements are quite close, and the deformation mode, the way that it's physically moving, is very close to what I'm doing in the background there. So hopefully that instills some confidence that what you were doing, and that you had exposure to this already. So that's really cool. I'll skip over, or maybe you guys did this one as well. This is a shear stress test where you're looking at a pin that's getting pushed from one side and sheared and kind of breaking off. I think, yeah, you can kind of see that a little bit here. This was done in ANSYS. Here's an example of some parts of an internal combustion engine, so fairly outdated technology, but this is looking at contact between different parts of what's called a connecting rod. So here's an example of a student that wanted to optimize. It's a two-force member effectively. I brought it through so you can feel free to pass these around, but they're different types. One of them has an I-beam profile, the other one has an H-beam profile, and they all have been broken in one way or the other. So this is often a way that you would kind of trigger an analysis in a five minutes. You think of the different components that happen, something typical that you see in an environment, and you want to figure out why. Here's an example of how that component would physically interface in a rotating machine. So you can kind of see how it's rotating and we're converting that rotational force or that rotation into reciprocation. So that pin is moving up and down there. Here's an example of a different student that did a similar project and they wanted to fully optimize kind of the geometry of that particular component. So you can kind of see once these get passed around how similar some of the features on this look to what you're going to be holding in your hand. This is kind of the process flow. So the student wanted to mass optimize this baseline geometry that they had here. And they said, okay, well, let's put a lighting hole. Okay, so we went from 95 grams in this case. This is not that particular component. Those are about 450 grams. So this is from a much smaller system. And we dropped about 6 or 7 grams here by doing the first design optimization where they just arbitrarily put a hole. And then they said, okay, well, let's change the size of the hole because this now caused some stresses that were too high. And you can see how they've evolved over time. They've added some mass back, they reduced some more, and then they kind of fully optimized design there at the end. This is how it's set up in the analysis world. So you can see that there's geometry. We'll explain this in more detail in about 10 minutes, but there's some geometry that all of you have had exposure to. Then you discretize that geometry into mesh elements, and I'll talk about why in a little bit. And then you apply different boundary conditions and loading to those mesh elements. And here's some animations of different design revisions that the students looked at. This is all student work. They did this in about 3 weeks of taking a course. And this is actually this is probably the weakest student in the class. So I'll give you an example of some of the better students. This is a student that looked at the thermal stresses inside another component, and they said the top of this is exposed to combustion, and we want to look at the temperature distribution across the top face. So here you can actually see temperature values. Okay, so you can see those in different locations on the left, and then the right is stresses. Here's an example of a topology optimization of kind of a similar component that everyone's passing around here. This was probably the most second most proficient student in the class, where they looked at a crankshaft and they wanted to understand the vibrational characteristics of it. So you can kind of see here how, if you've ever played with kind of a guitar, you might appreciate that when you strike an object that can vibrate, often it makes some noise and there's a characteristic frequency at which it moves. This is effectively what it's doing, except it's not a guitar string, it's a rotating component and it's made of metal. So here's an example of an optimized design that they did. This is probably the most proficient student in the class, or the best student in the class. They looked at a crankshaft and they wanted to simulate and do a topology optimization to remove as much mass as they could from it. Here's an example, and this is their ending design where they removed a ton of material in location where it didn't need it. Okay, so that's something that's pretty cool. Here's their initial model where they started with fully cylindrical kind of part, and then they turned it into this mass optimized version. And then they analyzed it to qualify that it would meet structural requirements. So they looked at not only the amount of deformation, but the amount of stress in the component. So I guess that's the ending of all of the sexy pictures that I'm going to show you. Hopefully you can appreciate some of it, but question. Excellent point. So they did do that. I didn't put the slides in here. That's often one thing that people overlook when you remove mass from something. Not only you're changing the polar moment of inertia, you're changing the center of mass, and often components that rotate are balanced to a certain geometric property because their center of mass is in a certain location. So often when you remove a bunch of mass, it screws all of that up. So yes, they did do that. I didn't bring those results here just because I've already gone through like 45 slides and I don't want to bore you with that. But I'll post or I'll give your professor or your TA the PowerPoint version of this. It's like 200 megabytes just because it's um, a lot of animations and videos. The PDF you should have access to already if you're following along with that QR code. Any other questions? Yes. Yep. That's an excellent question, and the answer take a while to properly describe, but it really depends on what you're trying to analyze. Okay, so if you're doing thermal properties of a microchip, a casing or something, so potentially if the temperature distribution, or let's say the area of interest that you're concerned with is accurate, and you have some testing that corroborate that, that's good. But if there's parts that are somewhere away from it that have really low temperature that aren't perfect, is it something that you need to correct? Okay, so that's the first question you need to ask yourself. And for those of you that might not have heard, it's an excellent question. That how do you correct? How do you course correct when you have an issue? There will always be issues. I want everyone to get the idea of perfection out of your mind. It's about is it correlating well enough to your acceptable tolerance. Okay, so the first thing is like looking at the amount of energy that's moving in and out of the system. Okay, if you see in this case that, or say you get a non-sensible temperature, like you're expecting a temperature to be 200 degrees Celsius and you get 2000, where is the heat generating coming from? Where is that extra energy coming from? So first thing would be to kind of understand what order of magnitude, and then from there, okay, is the way that the heat source and the heat sinks in that case in the thermal analysis procedure, is are they in the right spot? Do they have the right magnitude? Is the flux correct? All of those things. Because maybe you're overestimating the source. Maybe you're saying that this is a 30-watt device and it's dissipating not enough, but is it really truly operating at 30 watts all the time? That type of thing. Is the enclosure, is the ventilation around the enclosure, is that something that you're accurately modeling compared to the test setup? Or is it just in stagnant air that's not moving? So is there free convection? Is there things you want to investigate? Are the boundary conditions, meaning all of the constraints that you put into your analysis, are they not only valid, but are they accurate? Okay, so we'll talk a little bit about that when we do the demo, but it's an excellent question, and it really depends on the type of simulation. You'll gain a lot of that confidence with experience. Sometimes you'll learn this by best practice, or there might be a standard operating procedure at the company you kind of work for, or even personally when you're doing it for a 41 project or something like that. You don't really have a good solution, but you might have test results that say, okay, I'm undershooting my temperature target or my temperature experimental value. Why is that? What ingredients to the model will make the temperature go up? Which ones will make them go down? And then you kind of tune it from there to suit. But it's an excellent question, and even now I don't have a silver bullet answer for you. It really takes time. And before you share results with someone, make sure you can defend kind of position. So given the time constraints, we thought that ignoring convection around the enclosure would be something that's reasonable because we don't have information about that. And we wanted to simulate the worst case scenario if there was no airflow. So yes, our simulation is overshooting the temperature a little bit and we're not truly accurate, but it's a worst case scenario. That's a good justifiable reason. So I guess now we'll talk about the actual background information now that I've hopefully wooed you with some sexy photos. Not those sexy photos. Okay. So in SolidWorks, there's different domains of simulation, And ignore the kind of marketing jargon here that says SolidWorks Premium, Professional. Those are the different uh, classifications of licenses that you can buy. But we'll go through most of these because you've already had some exposure to them from the animations that I've shown. But a static analysis is something that provides a tool for what's called linear stress analysis for different parts or different assemblies that are loaded by static loads. So that's the equivalent of here's a table, it has four legs, now I'm putting my weight on it. Okay? I'm not changing my weight, I'm not jumping up and down, I'm just applying a one-time loading to it. Okay? And it's a static event, meaning that you can take a slice in time and say that the forces are in equilibrium right now. Okay, I'm pressing on this table, and the reaction forces are holding me in equilibrium. So some of the questions you might ask yourself to determine what type of simulation might require, what type of problem might require the simulation is, will my part break under normal operating loads? Or something like, is my model over designed? Okay, so is this table much stronger than it needs to be? To support sheet of paper, yes, it is. To support potentially someone dragging the table to turn off, stand on top of the table and turn off the projector, maybe not. So it depends on kind of the context of the problem. And can you modify the design to increase the safety factor? And I'll talk about what the safety factor means. You probably already have had exposure to that to some degree. So the next slide here, we'll look at a different type of analysis. These ones are dynamic studies. So this is a similar simulation, except now it's a time varying event. Okay. So typical examples of this could be like something like a shock load. So if I wanted to take a sledgehammer and I wanted to slam it against this desk, obviously it's a pretty difficult thing to simulate because but I don't know what would happen when I put a sledgehammer to that. But now the event is time varying. There's an impulse, a force, and a whole bunch of inertia that's going to get imparted to the surface of this, and it's not an equilibrium event. Okay, so that's really what differentiates these two. So things like components that are mounted in vehicles, rotating machines, turbines, anything that's exposed to an oscillatory force, things like aircraft components, things that are loaded in a random fashion. So even wind turbine blades would kind of be something like this. So typical questions that you might ask yourself are the mounts of my particular component loaded by shock loading when it hits kind of a large pothole in this case, which is what I'm showing up here. This is a suspension component. If you hit a very large pothole, this is what would happen. Sorry for the bottom statement being cut off, but it says how much does it deform under these circumstances? So if you hit a really large pothole, it might bend something underneath the car, but is it going to allow you to continue to drive home or at least drive to a service center to get the component replaced? Or is the wheel going to be totally sideways and you can't actually physically roll the car anywhere? So those are things you need to kind of ask yourself. A motion simulation is enabling a user to kind of analyze the kinematic and dynamic behavior of a mechanism. So let's say you don't want to look at the individual stresses in something, you just want to look at the way things move. So you might have a bike and you're looking at the front and rear sprockets in the chain, and you just want to see, okay, well, what are the forces in these different links of the chain? How much inertia is present when the chain is rotating under this loading condition and this particular rev or speed. So even in a robotic arm assembly or in robotics, this is really popular where you might want to kind of size an actuator to be able to move a component, okay, based on the forces that are required and the linkages and all of the system kind of geometry. Also to kind of optimize, is the mechanism efficient? So if you think about even the Paralympics, they use a lot of, let's say, uh, devices that enable people that have some, let's say, difference in the way that their body anatomy is, and making that as efficient as the human limb might be something that they're trying to target. Okay, so if you have one of the bionic legs that can spring back or something like that. You want to make sure that is this the amount of energy you're putting in, is it similar to kind of the baseline target case? Fatigue is something that a lot of people don't really concern themselves with, but my last 10 years at the university have been kind of consumed by this one topic. Um, and it's very important because it kind of analyzes the resistance of a part or an assembly or anything really that is loaded repetitively on a long period of time. So this is a cyclic loading event where you have, let's say in this case, there's a car that's driving left and right on this proving ground type scenario, and you're gathering all of these different forces and moments and all these components that are deforming something. Not to the point where it fails immediately, but you're accumulating damage slowly, slowly, slowly. So typical questions that you might want to answer in this type of study are, can the lifespan of my product be estimated accurately? And I will apologize. Part of my research in fatigue is enabling people in consumer electronics in the automotive industry in a lot of these different domains of engineering to engineer products that fail almost fairly consistently. So you might have noticed that people always say things are not built the way they used to be. We live in a disposable society where the warranty period of something is kind of what it's designed for. And they mass optimize components, they cost optimize components, they optimize the manufacturing processes to be as sustainable and kind of renewable as possible in most cases. And often that leaves the consumer with a product that has a definitive life cycle. So this is another type of analysis that you can do. We're not going to talk about it. It's more of a grad course topic, but if you're interested in it, send me an email. We can have a coffee chat about it. Um, Frequency studies we talked about, and that offers tools for the analyst to kind of look at the natural modes and frequencies of a system, understand the way it would vibrate if it's excited by some random excitation. The typical questions that you might want to answer using this type of study is, will my part resonate or kind of move uncontrollably in normal operating mode? Are the frequency characteristics of my components suitable for the given application? And can I modify the design to improve that? So now we're going to look at some of the theory, and I'd like to start this theoretical kind of conceptual talk now with a slide that says it gives you a context of the length scales that we're looking at. So I wholeheartedly believe that to do this effectively, a multi-scale modeling approach is the way that makes sense. Okay, so your colleague here was asking, how do I know if my analysis is accurate? How do I correct it if it is inaccurate? And it really depends on the length scale that you're looking at. So on the very, very small end of the scale, on the quantum mechanics and molecular dynamics scale, we leave that to physicists as engineers. Okay, we're looking at kind of the bulk material, traditional simulation techniques. They do have simulations in crystal plasticity as well as quantum mechanics that you look at like the micromechanics of how things actually move, but we're dealing with things on a continuum basis. So we're not looking at the individual grains within the material or the individual fibers within the piece of wood. We're looking at the part holistically, kind of as a monolithic material, and we can even scale it up to kind of this assembly system level. So we're working in kind of the millimeter to meter range when we're looking at the scale. If you have a failure that you're kind of concerned with and you're like, how do I model this better? Or how do I understand more about the intrinsic nature of what happened at this location? That's when you start diving down a little bit more. Or if you're not getting an analysis that correlates very well and you're saying, well, why is the case? Often you have to look deeper. So it's like getting a magnifying glass and zooming in more and more and more. So now after talking for an hour, I'm going to actually define what is finite element analysis, and FEA is the acronym that everyone uses. But imagine having this is a really simplistic example, but imagine having a brick road from your home to your mailbox. So a lot of you might live on at a house if you live in a house where It might have a brick driveway, and there's a bunch of bricks that compose a path to go. I know a lot of people don't have mailboxes at the end of their driveway anymore, but just take the example as it is. And imagine if you're one of those really wealthy people that has a curved driveway, and you can approximate that by a whole bunch of straight segments. Each of those bricks is a very regular shape that you can interrogate and understand the properties of it. But when you put them all together, it's allowing you to effectively break down complex geometry into a very regular shape that you can perform equilibrium Stokes equations on, or heat transfer equations on, Fourier equations on. So it really depends on the geometry, how complex it is, and that will dictate how many of these little elements you need to kind of properly discretize the geometry. Here's the process flow for the way that finite element models work. You start with some CAD geometry. So this is the case here. It's a simple kind of ring loop thing on a bracket. And you might want to say, okay, well, in order to make my life easier, I want to simplify it a little bit just so it runs faster. And I'm not too concerned with understanding all of the aesthetic nuances of this. Like you can see how this has nice rounded edges here. Okay. So I want to delete some of the rounded edges that don't affect the end result very much. Okay. So depending on how you actually load this one radius in here, this fillet radius, could be very important. So that one I want to keep, but all the aesthetic rounded edges I'm going to remove so I can simplify the geometry to make the mathematical modeling a little bit easier. And then what the mathematical model is composed of, in this case, is 4 particular elements, but sometimes it's more. So the type of analysis, that could be like the static structural, the dynamic one, the modal or the frequency analysis, the fatigue. It's the domain of analysis that you're working in. The next thing you need is the material properties. So all of the properties that govern the way the material behaves. So it could be the thermal properties, it could be the electromagnetic properties, it could be the mechanical properties, it could be the fluid mechanics properties. It really depends on the domain of problem that you're looking at. And then you need to look at the boundary conditions. So the supports and the loading. So supports meaning how is this particular bracket being held, and how is the load being fed into it. In this case, this is just a static problem. So the final thing, so kind of the fifth ingredient is your mesh. The type of elements that you're going to use. How many bricks are you going to use to actually compose this geometry? What shape are the bricks? Are they rectangular prisms? Are they tetrahedrons? We'll talk about each of those in a little bit more detail. And then finally from there, and this is the back end of kind of the software that a lot of people don't see, but I encourage you to kind of develop an appetite to understand it, is the numerical solver. So all this is doing, it sounds very daunting, but all it really is doing is performing those equilibrium equations at each of those integration points. So instead of doing a simple textbook problem where you have here's the force, here's the constraint, and here's the moment, here's the constraint, and do some nice analytical solution, you're doing the same thing, but you're starting in one boundary condition, and you're moving a single element over. You're just doing the force equilibrium on that particular element, and you're propagating the result of that as the input to the next element. Okay, and from there, once you solve the entire set of equations simultaneously, or once the computer solves this entire set of equations simultaneously, that's where you're really leveraging the power of the computer. Okay, so they're very simple calculations or repetitive calculations that are just performed many, many times on these elements. So fixtures, the next element of building a finite element model, or I'll talk about one of the ingredients of the finite element model. This is often called boundary conditions, but really it represents how the given model is attached to something. So is it fixed on a surface? Is it fixed on an edge? Is it fixed on a point? Is it allowing sliding between two components? Is it allowing rotation? Is it rigidly fixed? Is it welded? Is it glued? You need to understand more about the way that the physical part that you're trying to model is attached, and that allows you to kind of um, apply the mathematical constraints in the model to accurately replicate that. Loads are something that I think everyone can appreciate is an important ingredient for the model, where you're You're applying forces on surfaces, on edges, on points. It could be a torque, it could be a moment, it could be a pressure. You could even have different types of loads like gravity, centrifugal forces, thermal loading, like your colleague here was probably going to need in their housing analysis for that thermal event. The final thing is materials. So here an example of some materials that are available in SolidWorks. Um, Copper, aluminum, rubber, glass, wood. There's a whole database and library of materials. Here's an example of what it looks like under the steel category, which is a pretty common structural material. So you have a ton of different grades of steel in SolidWorks. When you click on one, it's asking you what type of model do you want to invoke. Okay, do you want a linear elastic isotropic model? So what that means is that material behavior is only defined between 2 points in a linear regime. So whatever the material properties are, if you double the load, it will double the stress. Okay, you're not actually getting any post-yield behavior. You might remember that from your materials courses. Isotropic means the properties don't vary in different directions. So a piece of wood, even though it's probably a real piece of wood, if you pull it adjacent to the fibers, or in this direction, or transverse to the fibers, you're going to get a different material response. If you ever taken a hockey stick, a wooden hockey stick, and you flexed it in two different directions, you'll notice that too. So there's different material models available, and then all the properties that you would kind of look up in a handbook are also here. So a lot of the hard work is already done for you when you just open up SolidWorks and you start to do a simulation because this data is already there for you. If you're dealing with something that isn't in SolidWorks, Ranton, I think you've all had exposure to that in the past. That's a really good material selection software. So here's kind of a Ashby chart that you probably remember of Young's modulus versus density of Grant from the Granta software that recently was purchased by ANSYS. So we don't no longer have a university license, but I think your professors can provide you with something if you're interested. Um, so yeah, that's the final ingredient. I guess the truly final ingredient is the mesh, and we talked about what type of mesh elements can you use, what shape are those bricks. So if we want to model this particular bracket, it's called a fitting here, but just think about it like a bracket. In this case, we can split this geometry because it's kind of like plates and cylindrical tubes all kind of meshed together. We can split it into these small, what are called tetrahedrons, and it's just kind of like a pyramidal type structure. And this can approximate the geometry of this piece quite easily. Okay, so that's helpful because you can see how when you map these tetrahedrons on the surface, it gives you this really unique way of tracing the geometry. Okay, if you had a component that was made out of like a piece of sheet metal or even really thin plastic, in this case, it might not make sense to have elements that have volume. So we can use what are called shell elements, and instead of tetrahedrons, these are just triangles now. So they have no thickness in the model, but in the mathematical part of the model, there's a defined thickness. Okay, so it's saying that maybe the thickness of this bracket is 1 millimeter. Stiffness, the bending stiffness of these particular triangular elements is actually going to be defined as having a millimeter thickness of whatever material you define. Here's an example of like a tubular structure that you might want to model using what are called beam elements in this case. So you can split all of these geometries into these beams, and these are just like cylindrical kind of elements now in this case that you can change the cross-sectional property to be cylindrical, box, C shape, whatever you want, but it's a different type of element that you can use for a different type of geometry. The terminology of mesh elements and nodes. Elements we already talked about, but mesh is kind of what's colloquially termed as the representation of all the CAD geometry using the elements. And that's what your mesh is called. And that's what it actually, when you generate a mesh in the simulation software, that's what you're going to be doing. Nodes are the points where all of the actual equilibrium equations, the Navier-Stokes equations, all of the physics equations are calculated at the nodes, and those are the corners of each of these elements. And that's the points at which everything's joined together. This is the really only theory slide that I'm going to give you. The rest of it is all, this is a little bit mathematical. You might remember kind of the way that three-dimensional stress state works. So a lot of you um, might remember in simple tension and compression, the stress is really straightforward to calculate. It's just a force intensity, meaning that it's force over the area. What happens when you have these complex shapes that now you want to analyze in a real world situation where there's tension, compression, shear, all of these things combined? The way that we actually look at this is using what's called von Mises stress. And that helps us to kind of make sense of this complexity by providing a single scalar value of an equivalent stress state. So it's combining these tension, compression, and shear stresses into a combined stress or an equivalent stress that has the same effect on the material as a combination of all these stresses. And this allows us to turn it into a scalar, which is nice and convenient, but it also is a theory of failure. If the stress exceeds a certain value, often the material properties will be published in von Mises equivalent stress. If the stress exceeds that value, typically depending on the situation, but it's kind of widely accepted that that could be the failure stress of the material. Okay? So it's penalizing and adjusting based on this equation here, which is effectively the equation of an ellipse in stress space, which I won't get into, but you should remember it from your second year solid mechanics course. But the equation of that is going to dictate kind of the shape of the yield surface, is what it's called. The thing that I really want you to understand from this slide is what's called a factor of safety. So you might have already had exposure to this, but when you get a simulation running and you look at the result, you might say, okay, my peak stress is 100 megapascals, okay? But I'm allowed, based on my material that I've chosen, the yield stress is 200 megapascals. Now the limit of the material is 200 and the maximum von Mises stress that I'm analyzing is 100, and my factor of safety is 2 in this case. That's the ratio between the two. You want to ask yourself, is that something that is appropriate for your application? Yes. Are the coefficients? They're not empirically derived. Actually, sorry. Yes, they are empirically derived, but if you equate them in ellipse, and the reason for that one stress when you actually move the material, it kind of takes this elliptic shape. So it is empirically derived. It's based on real failure von Mises observed back in the 200s. Depending on the type of, let's say, component you're analyzing, Fresca is another type of stress, TRESCA, which is another indicator. For things like pressure vessels, if you're working in oil and gas industry, often they use that particular criterion a lot more. So some of the assumptions in linear and static analysis, this is what we're going to be doing today in the demo in about 5 minutes. But a linear analysis means that when you apply a force, you get a displacement. If you double the force, you get double the displacement. The response is proportional and linearly proportional to the input. That's what it means. Okay. It also means something like the material is also behaving in a similar way, but the deformation is behaving in a similar way. Just like a diving board. We're going to be doing a similar example like that, but a diving board, when you start to move it, it behaves fairly linearly because of the small angle assumption. Okay. Sine, cosine, and tangent at very small angles of rotation are very similar to one another. So that's not a big issue. But if you put a really heavy person on this diving board and there's a ton of deformation, now all of a sudden that small angle kind of assumption breaks down. So that's the difference between small and large. I know this doesn't give you a quantitative value for it, but SolidWorks will actually warn you when you have excessively large displacements, because maybe you put an extra zero on the amount of force that's in that component, or maybe you accidentally selected the material as being plastic instead of steel, and it's going to say, okay, well, you have excessively large displacements. Do you really want to do a static linear analysis, or do you want to do a dynamic nonlinear analysis? Is this really what you intended to do? And then you say, oh, yes, actually, I didn't know that the displacements were going to be that large. I should do a nonlinear analysis. or oops, I made a mistake. I put plastic in as the material. Let me fix that. And now it's just a typical linear thing. I would say that for most of the parts that you're going to be dealing with, it's going to be a linear static analysis just because of the fact that that's the most simple thing to do, and it probably has the highest factor of safety. Okay, you're not going to break the diving board if a child is bouncing on it. The moment you put a very heavy person on it is when it's going to kind of approach its large amount of deformation state. So here's an example of a spring that's in compression. So this file, I think I've embedded it here into the PowerPoint file. So when I upload that, you'll be able to get it as well, but you should have access to it if you downloaded the link from the QR code. Did anyone get that to work? Perfect, okay. So this spring, we want to calculate the stiffness. So I've given you the CAD file, and we just want to look at the spring is made of some material, it has some geometry. We want to put some loads on it. I've actually given you the file where those loads are there because I just want you to get used to processing it first, and then we're going to look at the results. So I'll bring up SolidWorks here really quickly. I had another analysis here that I was running, but we are going to open spring. Depending on where you save it, if you save it on a cloud directory or something with a really long file path, SolidWorks might complain when you start to mesh it because it has to put temporary files in the folder that you're actually working from. So just keep that in mind. You might run into some issues, but here's an example of a spring, and there's a top and bottom part here that's kind of like the faces that you're pressing on. So the SolidWorks modeling part, we're not going to go into because I think a lot of you already know that. But in this case, I've set up an analysis here for spring stiffness where we've actually added a fixed boundary condition on the bottom here, meaning that we're holding the bottom fixed. It's as if it's sitting on the table, and we're applying a load on the top. What happened? Oh. And we're applying a load on the top. In this case, I think the force I've applied is 0.1 newtons. Okay, in this case, we want to calculate the stiffness of this spring. So we're applying a small load, and we are going to push down on this. I want someone to think critically. Obviously, seeing the answers on the screen might not understand what's going into this yet, but I want you to think critically. If you took the spring and you put it on the table, you push down on it with your thumb. Okay, you probably got this before, and you're thinking for granted. But what do you think would happen if you push down on it? It will compress. What if you didn't have your thumb perfectly aligned? What would happen? It would fly away off the side of the table. Okay, so that's the most critical mistake or oversight that a lot of students make is that if you don't tell the solver to suppress or stop something from happening, it's a valid physical outcome from the simulation. So in this case, if you're pushing down here and you're holding it here, it's fine the moment you start pushing down, but the moment there's any movement here that isn't perfectly symmetric, that thing's going to want to fly out to the side. Okay, so we need to force it to move only up and down. So we're adding what I call an additional cylindrical constraint on this top face here to force it to move in this kind of cylindrical path. Because we only want to force it to you might be very careful when you're pushing down the string in your life, and you're like, I'm going to be super careful. I'm only going to push only vertically. And in this case, the forces are perfectly vertical, and the constraint is perfectly vertical or perpendicular, so it's not a big deal. The problem here is the curvature of the spring and the fact that it's not totally symmetric in where it starts and where it ends. So that's the issue here. That's why it's going to blow out to the side. So I'll show you. Once you have the CAD model, you want to create a new study. Okay, so we're going to go through this step by step in the next one. I'm just going to show you the ingredients here really quick. And when you do that, it's going to ask you, do you want to do a linear study? Do you want to do a dynamic study? Do you want to do some form of other study? And in this case, we have a spring and we have assigned the material to it. So if we right click over here and we click apply edit material, it'll bring up the material database that in this case we've selected alloy steel. So everything here is already set up for you to run. Okay, the only thing you have to do is actually mesh the component. So it's as simple as going down to the mesh tab here, and we'll say create mesh, right click, create mesh. So if you want to follow along, this is really the only step you have to do. And you need to now ask yourself, okay, well, there's a slider bar here between coarse and fine. Okay, this is actually defining the physical length of the amount of bricks that are on our driveway. You can think about it like that. Just for the sake of running this in front of you during the lecture here, I'm going to put it all the way to coarse, and we're just going to see what happens. As quickly as possible. So I will click enter or the check mark, and there should be a dialog box that pops up, and it's going to start messing with the component. I will now take a moment to actually mesh it, but as my in my time professionally as a engineering analyst, I spent weeks, if not months, of my life to get good quality components. Using this type of approach, like just an auto method, it's kind of you kind of get what you pay for. Sometimes if it's simple geometry, it looks really good. We'll see an example of that. Sometimes it's terrible in the results. You have to go and touch it up a lot. And I'll show you ways of kind of influencing the mesh to do what you want and capture the geometry perfectly, or as perfect as possible. So we're almost done here. Does anyone have any questions while we mesh that last 1%? It's almost done. It took about a minute to run this when I did it last night, but now that I'm recording this kind of session, I think my computer is a little slower. But you can see the history. This is what's called the history tree on the left in SOLIDWORKS. When you're in the analysis mode, it's very similar to the way that you operate in the CAD world. It defines everything here for you. All the ingredients of the model are laid out on the left. So now we can see that the parts that are really simplistic, it's assign these very large tetrahedrons to that, and the spring, because it has this kind of small wire curvature geometry, what the auto mesher decided was this element size. So this is the coarsest possible that we can get using the auto mesher. Okay, so that's nice. We'll align this to be looking like that. Okay, so we can easily see we have all of the ingredients to the model here. We have a defined material, the material property. We have a fixed constraint on the bottom. We have a force applied at the top. And these parts, I know you didn't really see that, but they are actually connected here. So you don't have to worry about defining any contact between the spring and this top part. We just model it as being connected. So that's pretty convenient. And everything is steel here. And we've actually created our mesh. So we have all the ingredients that are necessary to run the analysis. And if we go up here to the ribbon where it says run this study, we can click that and another dialog box will pop up where it's running. And this will probably take about another minute, I think. But some of the results by default that'll come out of SOLIDWORKS, you'll get a displacement plot. So that'll tell you about how things are performing. You'll get a stress plot, and you'll get a equivalent strain plot. You can change the quantity of the stress that you want here. So this is the cool part. People like seeing this. This is the stress, which if this was a first, I teach this type of example to a first year class and they have no idea what stress is. So we immediately jump to displacement, but you can appreciate stress. This one is pretty intuitive, okay? Red is levels of high displacement, blue is levels of low displacement. Going back to your colleague's question here, how do I know if my model is correct and how do I correct it if I have something wrong? We've applied a boundary condition here at the bottom that fixes the bottom of this. So we know that it shouldn't move. And we're seeing that this blue color here is 1 to the -30. So very, very small number, infinitesimally small millimeters of displacement. And the top is 4.18 e to the 0, e to the 1 millimeters. So if we go back to the PowerPoint really quick, where it's asking us what newtons per meter. So we'll go back to SolidWorks and we'll look through a few more things here. A lot of what people like to do in a simulation, if you go to plot tools here, you can actually animate this, and this gives you the nice deformation. You can change the amount of steps that are here. You can change the speed. You can even save it as a video. So you save it as an AVI file here, and you can save it as a video. So that's an example. The other thing that people might think, oh, well, the stress of this inside and find a particular spot here and see what the stress is. So you can do that by going to plot tools and actually probing. So left click and you can actually select an element and see the value of the stress there. Okay, and we can see the value of the stress here. So 7.55, 7.22, slightly different, but on the order of 7 megapascal. That's where E to the 6 come in. So not very high stress relative to the failure stress of the material. We can actually look that up in this case, and we can see, okay, with 0.1 newtons, what's our factor of safety? Oops, not a fixture. I wanted to go back to the material properties here, edit the material. And in this case, it says the tensile strength is 723 e to the 6, basically newtons per millimeter. So our factor of safety is around 100. Okay. So we can change the material and see the difference in the actual component or the deformations that we're observing. But really simplistic example, your stiffness should match okay, maybe the diameter of this spring is a little bit different. Or maybe the cylindrical constraint that I put on it is not totally accurate, okay, but it depends on your tolerance of accuracy here. So that's kind of the first example here. And you can see the animation that you get when you export the AVI file. Absolutely. Good question. The answer is it depends, and it's a good question because if you're only considering the spring stiffness, these parts will be totally rigid. If you make it out of plastic, it's going to contribute to the overall displacement. So it's a good point. Because this is so bulky and large, ideally I would have assigned it if it was rigid. We could go back and do that in the running analysis to see that it won't change very much. Because relative to the spring, this is effectively rigid. Okay, so that's a good point. You want to look at, well, what's the part of the model that is actually relevant or part of what I'm trying to figure out. It's just the spring in this case. Yes. My understanding is that like you're applying constant force, and so the animation just naturally go from like initial position and then like time step like the next one is like all the force and then it just goes to the equilibrium and stuff. Yeah, excellent question, and I didn't explain that well enough, so I'm glad you brought it up. There's a way to change the deformation scale here, because obviously this is moving a lot more than the spring would physically move in real life. You might not have thought that, but in this case, to exaggerate what you're seeing when you force it to animate, it makes the displacement scale larger. So it amplifies it. If you go to true scale, you'll see that, and you click the checkbox, you see that this is the actual amount of movement that's here in this case. So not very, it's about 0.4 millimeters. Okay. And when you animate this, all it's doing is taking the first step, the last step, and it's linearly interpolating between the two, and it's saying I'm inserting 150 images in between, and that's all it is. When it's a linear analysis, it can do that quite easily. When it's a nonlinear analysis, it has to actually solve every step of the equation. So it's moving a small amount, solving, moving a small amount, iterating a solution. In this case, it's just a single step. So when you animate this now, because I've changed the deformation scale to be true, in this case, it's still showing a large amount because that's what the animation generally is for. Maybe I didn't save. Yeah, see the deformation scale there was still 14. So double clicking on this and changing it to true scale or user defined, let's say, and I click enter. Now it's 1. I think when I go to animate, it's going to stay as 1. So you can see this is the true deformation of how much the spring is there. I guess I didn't click the checkbox before. So you can change it to whatever scale you want. Often the structures are not going to have visible exactly. So the resting state is 0 load. That's the first step. And that it's 0 step, I guess step 1 is just under the full load. And then it's going back to 0 and oscillating. Okay. Next slide. So exercise 2 is this L bracket, and we're gonna kind of put this thing into bending and see what happens. So it's going to show us a few things. It's going to add some importance to mesh density because we just kind of arbitrarily used the auto mesher, which is the last one, and we're going to say, okay, well, what happens when we have this fillet here? Because if you put a constraint up here and you put a load on the end of this L bracket, it's going to bend about this point. I think intuitively everyone realizes that you need some form of fillet radius there to prevent pretty big notch concentration factor, stress concentration factor. So this is the way it's set up in SolidWorks. It's a simple fixed constraint on one end. We're going to apply 900 meters, and I've given you the model for that as well that you can open up and check out. And we're going to look at the results in a second. So I'll pause this here so it's not going ballistic. And we'll open that L bracket model. So in this case, I provided you with a bunch of different meshes already. So there's a few tabs on the bottom here that all have different mesh setups. But what I'm going to do here in this case is I'm going to delete this fillet first, and we're just going to mesh it ourselves. So I encourage you to use mesh 4 here because this is the one that's set up. And I will go back to the model, and I'm actually just going to right click on this and suppress it. So it's going to turn this into a sharp corner, and we'll go back to mesh 4, and you can see that now these have these small X's here because now it's out of date. Our time has changed relative to our mesh, so it's going to tell us you need to redo something here. And it's actually going to show you that your results are out of date. So mesh 4, we have a fixed constraint at the top here, and we want to apply a load here. In this case, there's nothing that's if you fix it at the top of that face and you put it down there, it's just going to try and bend that thing. It's not like it's going to buckle to the side or anything weird like that. So it should converge and run like this. And our mesh that we're going to do, once again, we right click on the mesh here. We click create mesh. And we're just going to slide it to coarse again because I want this to actually work right now. And you can see it gives us these nice coarse tetrahedrons, and there's pretty large elements at the edge of this particular shape here. Okay, so we'll click run because we have all the ingredients we need. This is once again work. It's thinking in the background. What's it asking here? One more. Let's try this one. Oops, I think I had this open already. I need to reopen it. So I think I'm trying to overwrite the files from when I previously opened this. So I will close this and reopen it. For you, it shouldn't make this issue because you have a fresh set of the files. Okay, so we will suppress this. We will create the mesh. And you can see under the mesh toolbar, there's a warning here that you can say, issue a warning for distorted elements. If we wanted to like make it slightly finer, in this case, we could do so. It'll take a little longer to mesh. And now I think it's placed 4 elements across the thickness instead of 3. You can play around with that and do it a little better if you want. So in this case, we want to rerun. What's wrong? I guess it doesn't like what I did with suppressing that fillet. So let's just open it back up the way that it is. So you're who is an idea of if you had no fillet here, what would be the stress when you start bending this? As you get closer to that edge, what happens to the stress? Who is an idea? You're bending this component, and the stress is kind of there's a large bending stress in this notch here. Who's an idea of what will happen as you get closer to that edge? Well, in this case, I think it's fairly intuitive. Let's see if the answer. Why is this not mesh? Create mesh. Let's try this again. It's meshing. Okay. So now we've done it with the fillet, and you can see how much extra element density is put right in this location here. It hasn't really affected anything outside the end, only where we have a small radius now. It needs to have a certain amount of elements here to capture the curvature of that. And you can see how nice it's decided to do that with 5 elements across this one little radius. Okay. So now we'll try and run this, and hopefully it runs. Otherwise, there's something wrong with where I downloaded the files. Okay, so I'll let this run in the background and I'll jump to, because this will probably take a minute or two. I'll jump to an example of what I was trying to say here. If you have this type of geometry here with no radius, what happens? What's the stress here? Is it higher or lower? The stress right? Who has an idea? What would you think? Is the stress out here? If you're bending this and pushing down, the bending moment goes up. If you remember from the solid mechanics class, the bending moment will go up as you go closer to the here. So theoretically, as you going to get a higher and higher amount of stress as you go closer to the set. So this is kind of an example of where mesh density makes a huge difference in peak stress. So in this case, changing between these three meshes overall has no influence really on the displacement, the amount of movement that you see at the tip. However, and you see that the difference here is about 0.4%, next to nothing. However, the von Mises stress goes up by like a factor of 2 in this case, or more like a factor of 3 almost. And the reason for that is as you make the element smaller and smaller, you're capturing more of that really that area that's really close to the edge where the maximum stress will occur. Okay. So let's see if this finished running. L bracket. Yeah. Okay, so here we go. And we'll turn it to the side here to show everybody the intuitive kind of behavior of what we would expect. Let's look at displacement first because I think everyone would understand this plot. This is kind of what's happening when we're deforming this. And you can see it move up and down here. But this is the area of concern that we were actually looking at was the corner of that radius. We've added this fillet in this case. That's not what was showing in the PowerPoint, but this fillet is actually where the hotspot is in terms of stress. So relative to the elements beside it, we'll pick off by doing plot tools, probe, and you can see if we look at the stress here, it's about 34 megapascals, and the stress here is 98 megapascals. So there's almost a factor of 3 difference between the two. Okay? That's something that you want to accurately, because if you think about the way that this part is actually deforming, those are the things that's where it would break intuitively. If you're gonna apply a load downward here, intuitively that's where it would break. If we increase the mesh density even further, you're gonna have even better. Okay. So there's one more example that we're gonna go through. Here's showing a plot of increasing the mesh density without the fillet radius has the effect of increasing the peak stress. Just to be complete, hopefully this runs quickly enough, but let's redo our mesh. So we'll right click, create mesh, and it's saying remeshing will delete the study result for mesh 4. That's fine. The mesh is or the results are intrinsically linked to the mesh. So let's change it to somewhere about there and see what happens. So you can see not only, well, the mesh density in here changed a little bit, but the majority of the change was in the bulk area surrounding everywhere else. So if we rerun this, who has an idea of what's going to happen to the stress in this case? The film will change a little bit, but the rest of the area, I think it'll be dramatically different. I don't have the file to compare back and forth, so it's going to be hard. So overall, the shape looks very similar, okay? But we'll look at it in more detail in a second. So there's still stresses on each of the sides here because you're bending the thing, and there's still the peak stress in this area. So we will look at probing this again. I don't know if I'm clicking on the exact same element, but it's about 33 and about 99. So pretty much exactly a ratio of 3. The reason being that this didn't change very much is the only place where changing the mesh density would have an effect is when there's a high gradient of something. Okay, meaning that there's a high rate of change between the difference between the stress here and here is next to nothing. So if we join all of these elements to one big element, it still would be technically nothing. But if we put more elements here, we're going to capture the gradients of stress a lot better. And so that's something you need to keep in mind in the back of your head all the time. So the final kind of example that I want to work through in the next 10 minutes is I'll jump back to those in a second, is this diving board example here. So I'm not going to give you the file because but it's asking you to effectively make a rectangular prism that's 10 inches long and 1 inch by 1 inch in cross section. Just a square, sorry, a rectangular prism. It's a diving board with a weird aspect ratio. Okay, it's saying create a static study, make it alloy steel, fix one of the faces, and kind of turn it into a typical diving board problem, and apply a downward force to the upper end or the other end with a magnitude of 100 newtons. Okay, it's also giving you the theoretical formulation of how to find the displacement of the fit. Okay, so we can do that as well, but I'll leave it for you. But we're going to create this quickly in SolidWorks. So now we're going to be doing it from scratch. I'm not going to be giving you the file to do this. So if you click File, New in SolidWorks, it's going to ask you, do you want a part? Do you want an assembly or a drawing? It's just a single part. It's a simple rectangular prism. This one I encourage you to work along with because it's really easy to do. So we're going to do a front plane sketch. And I'm going to go through this really quick because I'm assuming you know how to use SolidWorks at least a little bit. But all we're going to do is create a box here and make the side lengths 1. So it's asking us to do this in inches, I think, or so we're going to change the units on the bottom right here to go to inches, pounds, second. And we're going to redo the sketch because the moment we do that, we have to redraw it. So we'll go back to the front plane. We will sketch on that plane. Now that we have our units set to inches, I'm going to arbitrarily draw a rectangle. I'm going to set the side length here to 1 inch and the other side length here. This side length here to 1 inch. So we have a square cross section. I'm going to exit the sketch. I'm going to go to features and I'm going to do an extruded base or extrude this sketch, and I'm going to go 10 inches into the page, into the other direction here. So sorry for going through that really quick, but not really the focus of this particular talk. Everyone should be able to get to that stage really easy. So once you have a geometry, it's as simple as creating a study by going to the simulation tab here and going new study. So left click, new study. You can name the study whatever you want, but here's where the options exist for all of the different types of studies. Thermal, buckling, nonlinear fatigue, all of the things that we talked about before. But in this case, we're just going to pick a typical static study and we'll say okay. And now it's going to invoke all of the mathematical kind of framework for a static study. And the first thing we need to do is apply a material. So we'll right click on the part. Who has an idea for a material? It said steel, but who wants to? In this case, steel is what comes up, but let's make it out of wood. If there's here woods, let's say it's a pine, mahogany. Okay. Following problems are detected, please. I don't think there's any material properties for mahogany, unfortunately. Yeah, it just gives you a mass density. So that's a good, yeah, I'd like to get fancy with it. That'd be cool, yeah. Maple, let's see if any of the woods here, let's see, maple. Balsa has material properties. Okay, we'll use balsa then. Not as fancy, but still somewhat fancy. Okay, good question. We're going to right click on the part. And then it's the very first. So you could also apply your favorite material, and you can impress people at parties by entering in all the mahogany details from MatWeb into SolidWorks and then making your own custom material and then having it as your favorite material that you then can utilize for all of your simulations. But so you're gonna now visually it looks like it's balsa. The material properties are represented by balsa. told us in the PowerPoint that we wanted to apply a load and a constraint. So luckily, a lot of the process flow was kind of left to right in SolidWorks here. So what we want to do is under fixtures, we want to apply a fixed geometry here to one side of this balsa diving board that's oddly shaped. So I will apply a fixed geometry here. And then on the other end, you click the face, obviously, that you want the fixed geometry to be. On the other end, we want to apply a force. Okay, so I'm going to go to external loads, click on force, and you can see we're confronted with some options here. We can do a force, we can do a torque. But the most important thing you need to understand is that you have to define not only what direction the force is in, but the magnetic. So the way we can define and the surface it's acting on, or the geometry that it's acting on. So you can see when we hover over something, it's going to show us, do you want to apply the force there, there? We actually want to apply it at the end. But is that the correct direction that we want to apply the force if we're looking at a diving board type scenario? The answer is no. We don't want the direction to be normal to the surface. We want it to be in a direction that we're specifying. So I'm just going to say that it needs to be in this direction here. Okay, so I click an edge as a kind of geometric feature that I can use as a constraint. And you can also say, I want to reverse the direction to make it down, and we're going to apply, I don't know if it needs to be in pounds, so we'll change this unit system to pounds. And we will say 100 pounds. Very light individual. And we will click OK. And now we have our boundary condition and our force defined, which is nice. Okay. Because the only thing we need to do now is add a mesh. So we'll right click on mesh and we will hover up to create mesh and left click. And this one is a really simplistic geometry. So it really doesn't matter coarse or fine. It's pretty easy to arrange a bunch of bricks in this particular orientation to make this run. So I just left it as default. But intuitively, the result of this is a lot more simpler than the one we previous example. So I'm going to let this mesh. And I'm going to jump back to the PowerPoint to show a few examples of how you can simplify things. That example we had that we had might have been a part of a larger assembly that you know this part and that part is fixed. If I'm only concerned with the failure of the it might make sense to simplify the geometry to get rid of everything else that isn't a part of the physics that you want to simulate. So if we don't care about, say these were made out of titanium or something very, very strong, effectively they're rigid relative to the rest of this. We just want to look at how is this L bracket going to fail. So that's why we've extracted it from the large geometry. When you make these assumptions, you need to make sure that they're physically sound. So it really depends on the physical application. I said that there was an example of a student team. They used some finite element analysis. This is an example of a Formula SAE car that they looked at the torsional rigidity using beam elements of the frame. So here's a point state action that was applied to the frame, and you can see the amount of deformation right on the corners. So hopefully now SolidWorks is done meshing that. We shall check, and it has. So that's nice. We have our nice mesh, and we can go now under Run this study and click Run. And another dialog box will pop up where it's effectively invoking static equilibrium equations, starting at this boundary condition and propagating it through all of those elements. Okay, and it has to reach static equilibrium throughout all of them. So this is a good opportunity to take a warning from the system that says excessive displacement for calculating this model. If your system is properly restrained, consider using a large displacement option to improve the accuracy of calculations. Here's an idea of what material to select. Balsa is a very soft wood. So a 1 by 1 inch balsa diving board with a 100-pound person jumping on it is not going to go so well. So steel would work better, but what we can also do is say, we can lower the force and say, okay, maybe this is a diving board for cats or some pet even, I don't know. We can say excessive, click no to solve with the small displacement, click yes to solve with large displacement, cancel, and we're going to change the force here. Let's change it to 1 pound. So if we right click and edit the definition, maybe let's say 3 pounds. I don't know how heavy a cat would be. Garfield weight, maybe 3. Yeah, 3 is too small. I think cats are like 15 pounds probably. But let's see if this works. And we will rerun the study. We don't need to remesh because we didn't change anything about the geometry. So let's see if it flags this now. And you can see it started to run. So no longer is the displacement too high for this cat. So we get a very nice quick result because it's a very simple geometry. And we'll look at it from the side here, and we will plot and animate this plot again, kind of like what we did before, and you can see how this is moving up and down like you'd expect. We'll change the results here. The 3 by default that you get are stress in von Mises equivalent stress, which we talked about what that was. The displacement, which is just the amount of motion, and the strain, which is effectively describing the relative movement of the material to one another. So we'll look at the displacement. The tip displacement here is about 0.7 millimeters, so it's not a huge diving board jump. It's a small angle. One of the interesting things that I'd like to do is show you, okay, well, what happens when we go back to the modeling tab here? And what if I want to turn this into an I-beam? So I'm going to create a new sketch, and I'm going to take some cutouts out of this part here, and I'm going to say I want to create a sketch on this face, and I'm going to orient my image to be perpendicular to that face, and I want to create a cutout here, and I'm going to make a construction line in the middle of this to use as a mirroring plane to draw this faster. So I'll create that for construction, and then I will say, I don't know, an arbitrary dimension here might be between here and here. Let's say 0.1. You don't have to follow along to do this exactly. Actually, but I encourage you to try something specifically like this. So I'm going to make a mirroring plane for construction, and then I'm going to create a cutout. I'm going to make the cutout somewhat symmetric. So let's say this is 0.1 from all the edges. I'm going to say, I'm going to add a constraint between here and there. And then I'm going to mirror this. Oops. I'm going to mirror it about this, and I'll show you why I'm going to do this in a second, because I want to cut out these flanges to make this an I-beam, and I need to do it 10 inches in that direction, and you can see now I've turned our diving board into an I-beam. Okay, we've learned from that bending exercise that potentially these sharp edges are going to be a problem, so I will add some fillets here, 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 and here. We can click OK. And now I want to pose the question to the class. I'm going to go back to the static simulation, and you're going to see that our mesh here and our results have kind of this yellow caution mark on them. The faces that we've assigned for the strength and load haven't changed, but our mesh should change now because we've changed our geometry and the results clearly are out of date because now we have an IBM profile. So for us to remesh this, it's as simple as right-clicking, create mesh, and let's make it slightly coarse so it runs quickly. And our nice balsa diving board for kittens, not cats. Too small of a weight for cats. We'll see it mesh, and then we'll interrogate the results again. But the number one thing is I don't want people to feel like it's daunting to fairly simple. It's just you need to build up. It's like learning how to run. You can't run before you can walk. So now you can see in order to mesh this geometry because the features are somewhat thinner, you have a lot more elements. Okay. You can make this even finer if you wish, but we'll rerun this. So we can go to run this study. It's going to run in the background. So while that is running, I'm going to go and finally kind of summarize what we did here a little bit to conclude. We did a diving board example, and we looked at the diving board data and changed geometry a little bit. We did that in SolidWorks. There's also a cool support bracket if you want. I teach a grad course that intensively uses ANSYS, but ANSYS is a competitor to SolidWorks. You can get a license for it on campus, and the user interface looks like it was engineered in the 21st century. So it's a lot more intuitive to use, especially with the scholarly version of it. And here's an example of a bracket in ANSYS that we've modeled where there's a fixed support on this surface, and there is a distributed force here of 200 newtons, and it's an aluminum alloy bracket that has this cool geometry. But you can see the ingredients are the same. The model is the same. This is still a static analysis. You can see this is actually called bracket static stress, but button clicks are a little different. Every solver has a slightly different layout, a slightly different graphical interface, and even the methodology could be slightly different, but they all have their own kind of merits and drawbacks. In this case, we can see if I animate the image here, so I can change the deformed shape to say, okay, I want to animate the way this looks like, and you can see how the tip will move down, kind of like a diving board on steroids, just like what we were looking at before. This is made out of aluminum. This particular animation is not sinusoidally changing where it's going between 0 and fully deformed state and then back to 0. It's kind of jumping back. So we're probably going to ask the question, the way ANSYS works is a little bit different. But you can see that here's another example of something, and we can open, there's a bunch of different, I guess, example files in ANSYS that you can work with as well and do some static analysis in there. Let's go back and check to see if our SolidWorks simulation is finished. You can see that it has our nice I-beam profile, has a lot more displacement now. So let's check what that displacement is because we've cut out a whole bunch of material, and we will orient the image. So our displacement now, instead of 0.7 millimeters, we went up to 1.2, which is what you'd expect. But we've cut out a bunch of mass. So if you combine a whole bunch of these items underneath a larger surface, you could technically make a pretty mass optimized diving board. So there's a good example of that. Looking at the stress distribution, you can see that the peak stresses are kind of located in the area close to the fixture, which is what you'd expect. That's where the highest bending moment is. There's nice ways of actually looking at this as well. You can do what's called a section clipping to actually move this through the surface here and look at the volumetric strain inside. of the I-beam, which is cool. So that's kind of like a section cut just within the analysis software. An ISO clipping is cool because it can show you the parts of the actual design that are above a certain value of stress, and it can hide everything else. So in my opinion, these are the most structurally effective parts of that component. These are the ones that do the most amount of work because of stress and loss, which makes sense because it's the top and bottom sides. You can drag this slider around to include more or less stress, and it's going to kind of grow that area. So technically, this will kind of tell you if you were to have this ID and tell you that it should be, if you wanted a mass optimizer, it should be kind of tapered or tractable. You start really wide at the base where all the stress is, and you taper it, which isn't really typically how diving boards are made. They're typically and that's because you have to walk on the model tree. But if you ever look at like Olympic diving boards made out of concrete, typically they're made like that. So there is some validity to what we're seeing here. So yeah, I guess I've gone over by about 4 minutes, so we're going to conclude with this last slide here. I've made a bunch of tutorial videos as a part of the curriculum for a grad course, specifically in ANSYS, but I can give you all access to that if you send me an email after this. I don't mind giving you access to that. There's one that's on fluid solid heat transfer. There's one on steady state fluid flow through a heat exchanger with thermal effects. There's one on doing a transient simulation. There's one on doing a structural simulation with multiple different materials. And then there's one doing a static simulation like what we just did that you all should have no issue with doing. But hopefully if I've taught you one thing for the past 2 hours is to not be afraid of trying this type of thing. There's no real downside. You're not investing your time at the end of the day. Of course, it costs money to buy one of these licenses, but as a student here, especially if you're doing a fourth year project, if it teaches you something and you use it as an engineering tool to kind of guide your design, in my opinion, that's the best way to start kind of exploring this. So is there any questions? I'll leave this slide up with my contact info. Is there any questions on anything you guys have to work on class now? If you have questions and you can hang around until otherwise, thank you for your time. And if you have more questions, send me an email. Thank you. Absolutely, yeah, go ahead. Any other questions? Yes. Yes, you can. In software, this is a free version where effectively you're going to say, I run this normal static simulation, but I want to repeat the values from that simulation and thousand cycles, not 100,000 cycles. And it's going to look at a different set of real pockets instead of looking at the solve ratio or the last name it's going to look at the key parameters on the material, which is other information you have to program into. You can edit it. If you have questions on the stuff like that, you're going to corporate traffic, send me on that. I got my So what the students do, you can look bubbles the other way you can do is small because if there's no bending in this grade,